Hello students, welcome back. Previously we went through prime sieves and got some motivation on trial division. Yeah, in order to test for prime, we have to do some trial division of the square root of n. You can do it one at a time or up to 1 to n at the same time. And the latter method is called prime sieve method because we cross out composite and the numbers that sieves through must be primes. But then again, when we do some technical division test, those trial division tests, we would like to have some shortcut. One shortcut is technology, of course, but suppose that we are back in 1920s or something like that. Or maybe we are just doing this for math competition. We're just, challenging our brain to do these by just traditional computation, no technology computation. In those cases, these kind of criteria may help. Integer divisible by 2 or integer divisible by 5, just look at the last digit. The reason 10 is divisible by 2 or 5. 2 times 5 is 10. So last digit out and what's left is divisible by 10. So that's 0 modulo 2 or 5. So look at just last digit, whether that's 0 modulo 2 or modulo 5. In this case, this number is not divisible by 2 or 5. Divisibility by 4 or 25 are based upon 100 is 4 times 25. So take last two digits away, and then what's left is 100 times something. That's a multiple of 100. So that's 0. This part is congruent to 0 modulo 4 or modulo 25. So the remainder belongs here, 24. And further division, we get 0, so this number is divisible by 4, but not by 25. And then 8 times 125 is 1000. So we can take last three digits, and the rest times 1000. This one is congruent to 0 modulo 8 and also modulo 125. So cross those out and test only last three digits. And yes, and this kind of testing are more useful for 8 or 4, not for 25 and 125, I have to say, but still, these are the typical techniques. And then if you want to test for divisibility by 16, and then 32, and so on, what do you think will I have to do? I'll leave those to you. And also, if you want to get a rigorous proof, not just examples like those, then you can set up a power series base 10, a finite power series base 10, and then maybe you can do some inductive proof or something. I'll leave those to you. And those are the first type of divisibility test. Just looking at the last digit. Make sense to you? Next, the second type of divisibility test, and this time let's look at sums of digits. The first one here is something everybody may already know, or do you? I encountered many people, but most students knew about this already, so I assume this is familiar to you. An integer divisible by 9, also an integer divisible by 3, all you have to do is to test the sum of individual digits. Again, let's work out with examples. As for rigorous proofs, by setting off power series with some symbols, A0, A1, A2, those kind of things, I'll leave those to you. So, in this example, what do we have? 5 times 10 million, 7 times 1 million, 6 times 100,000 and so on. We can rewrite like this. Yeah, it's basically a power series, finite power series. And then decompose bunch of 9s plus 1. Bunch of 9s plus 1. And this is 9 times 1, 1, 1, 1, whatever. So all these are divisible by 9. So congruent to 0, modulo 9, and also modulo 3. So cross all those out, what's left? 5 times 1, 7 times 1, 6 times 1, those kind of things. And what we have? We just have a sum of individual digits. And then whether this is congruent to 0 or not, that's something you can take. For example, 2 plus 4 is 6, plus 3, up to here I get 9. And then 5 plus 7 is 12. And then plus 6 is 18. Okay, all right, up to here I get another 9. So I get 8 plus 8, which is 16. That's not divisible by 9 or 3 either. So this number is not going to be divisible by either 3 or 9. This is one way to do it. And is this the way our textbook author explained? I think so. But it's not my favorite way. My favorite way is to do it this way. And it may look a bit hard initially, but believe me, it'll make more sense, and then it can be extended over to a little bit more complicated situation more readily. First, let's just take last digit out, and what's left is 10 times these, and decompose this 10 as 9 plus 1. Alright, and what is 9? That's congruent to 0, so cross it out. So what do we have? These digits plus 4. Okay, alright. And then we can do this again. This 9 plus 1, times 10, but decompose into 9 plus 1. And 9 is congruent to 0. You see, 4 was there before, and then 2, I just took it out. Cross those out, and what do you get? These numbers, and 2 plus 4. Do it again, and then one more digit, 3. Do it again, and one more digit, 8. And continue until you run out of everything. Then you end up with sum of digits. This method is something I prefer, and this method is, I think, more readily transformed into the proof using all those symbolic expressions. Instead of those numbers, you can use A0, A1, A2, A3 up to AN as a power series. Good luck about that if you want to write about those formally. Me personally, I would not bother. If you understand those ideas through these examples, that's going to be sufficient. It's not a proof. No examples provide a proof. It's not a proof. I'll just demonstrating ideas. That's about it. Anyway, divisibility test type 1 is last digit, last 2 digits, last 3 digits, those kind of things. That's type 1. Type 2 is summing of the digit, and then we went through the easiest criterion. Divisibility by 9 or 3. Next, divisibility by 99 and also divisibility by 11. The sum of 2-digit blocks is divisible by 99 or 11. What does that mean by that? Look at the last example. 57,688,324. Last 2 digit, last 2 digit, last 2 digit, last 2 digit. And then, is this sum divisible by 99 or 11? That's the question. For example, what if we had more decimal digits? For example, we had one more. In that case, we have like this. We need 2-digit blocks from the right hand side. We have another one here. Then we have this. And then if we had another one here, then you're going to get like this. You see, you need 2-digit blocks. The reason Well, one way to do that is to this way, which I don't really like very much, but I think this is our textbook's explanation. So 24, and then next 100, next 10,000, next 1 million, increment of 2 digits, and then rewrite 100 as 99 plus 1. Next, 9,900 plus 100, and then 100 is going to be decomposed further into 99 plus 1. And this is one 990,000, and then 9,900, and then 100 is 99 plus 1 like this, by increment of 2. And then please note that this 99, and then all those are congruent to 0, modulo 99 or modulo 11. So cross all those out, and we have only these ones left. So last 2 digits, and then the next 2 digits, next 2 digits, next 2 digits, add up, modulo 99 or modulo 11, so that's the remainder. If those are 0, then we have divisibility, otherwise no. Let's see, is this kind of computation actually easier than trial division by 11 or 99? Well, good question, but that's because you haven't done a lot of long division in your life. I mean, nowadays we use long division only in elementary school, and afterwards you just use computers and calculators. But if you have to do some long division with 12-digit numbers, then yes, you will appreciate this method. But as I said before, that's not my favorite. My favorite is to do it this way. Take 2 digits out and then get 100, which can be decomposed into 99 plus 1. And then this is 0, so throw it away. So we have 24 and then the rest. And we can do it again. 24 was there before. Take away 83 and the rest. And do it again. Take 68 and then what's left. So we can do it recursively like this. And I think it's a little bit easier this way to understand. And also, this one is closer to the full proof. Anyway, sum of 2-digit blocks. Next, sum of 3-digit blocks, and those test for the integers divisible by 999, which is not too much of a deal. Also, integers divisible by a prime number 37. Now that one is useful. And 999 is divisible by 37, so it works this way. And this divisibility by 37, that one is useful. Here's an example. Take the last 3 digits, 324 out, and 1000 times that, and decompose 999 plus 1, and 999 is congruent to 0. So cross it out, and we get last 3 digits and what's left. Do it again, next 3 digits, and what's left. Do it again, we have 3 more digits, like that. And then sum of those, and then you can, you can test for the divisibility by 37. Now, is this summation and divisibility by 37 is easier compared with this direct division? Oh, yes. And also, you can do further simplification by 37 for each of those before adding all those up. So this divisibility test is actually useful. If you don't have computer or if you don't have calculator, this is an effective way. We have one more testing to go, but looks like we'll have to consider those in a separate video. We'll come back and discuss the last aspect. Stay tuned.